Okay, so my name is Ingrid Gregor. I am a researcher at the Deutsches Elektronensynchrotrons, DESY, in Hamburg, which is a national lab for material science and particle physics. And I also have a professorship with the University of Bonn. So we call it Unibo. So there is a I have also very strong links, for example, to Dortmund, and this is why I was asked to participate in this. And I prepared a presentation today on the current status of detector R&D, but I will definitely focus on stuff I'm working on, and I will not cover everything because 45 minutes is way too short to give any big overview. Nevertheless, I will quickly start with the detectors for particle physics. Detectors are extremely important for particle physics. Here you see a picture very long time ago taken, and which was actually a measurement which ended up in a Nobel Award, measured in 1972 with Gargamel. And there one can give a rough overview that detector physics is extremely important. So but there is not one type of detector which provides all measurements which are needed in particle physics. We actually need an onion concept in order to do the measurements, to do a combination of measurements with different kinds of technologies in order to get the full picture. And here is a rough overview what is happening. So we have typically a tracking detector for the measurement of the charged particles, such as electrons and photons. We have further out an energy measurement with a calorimeter, electromagnetic or hadronic calorimeter, which is there for measurements of photons and other particles and so on. And in the outer region, we have a muon detector. And then we can take signatures of the variance particles. For example, photons typically don't make a track in the tracking detector, except they convert into a charged particle, and then we get a measurement in the calorimeter, in the electromagnetic calorimeter. We have measurements of electrons and positrons. We can identify in the tracking detector. Muons are typically not really responsive. They make a small track all over the place, but we don't get an energy measurement. We can distinguish charged hadrons by their signal in the hadronic calorimeter, and so on. So we get different signatures of the different kind of particles, and then everything we will place into a magnetic field so that we get out of the curvatures of the track of the charged particles. We can also measure the momentum. So in the example, for example, of Atlas, this is done in a layered structure, so that you have in the innermost region a tracking detector for the charged particles. You can get the signals from the electromagnetic and the hadronic calorimeter, and the muons give a signal here in the outer region in the muon detector. And therefore we need to work on detector R&D a lot in order to optimize those detectors. We have then the tracking detectors, which can be silicon detectors, either pixels or strips. I will get into that in a moment. Or one can also have the gas detectors for the tracking detectors, but typically you find them more in the muon detectors nowadays. Then we have calorimeters, where we distinguish between electromagnetic and hadronic calorimeters, and two different kinds, but calorimeters I will cover not at all, because I will focus on tracking detectors. And then there are muon detectors, which, as already mentioned, the outside tracker, which is typically also a gas detector. So HAP stands as the abbreviation for high energy physics, and there is a lot of R&D ongoing these days, and not only at the DESY, but all around Europe we are doing, or all around the globe, we are working on next generation detector R&D. in various areas. So we need, for example, radiation hard silicon detectors for the high Lumi LHC, which is around the corner. We work on mixed pixel sensor technologies for future applications, but also for the high Lumi LHC. We are looking into new silicon strip technologies and so on. So there is a lot of things ongoing right now. And if one is interested in working on detector R&D, I think this is a huge field where one can find interesting applications and also can work beyond particle physics with that knowledge one acquires in particle physics. So behind everything we are discussing is an extensive amount of studies of all of these new technologies there in order to qualify them. And these are opportunities for the internship, but also for the master and the PhD thesis. Okay, so here I have an idea of a detector development cycle. So one starts out with a crazy idea for a detector. It could be, for example, in the example which I know quite well, the crazy idea is use glue to build the detector. Then one goes into the fundamental R&D. One has to go from the crazy idea in order to see if that really works with a detector. Here I have the example of a measurement we did in the collaboration to see if our detector is radiation tolerant enough in order to survive the high Lumi LHC. So the dashed line here is showing the fluence, which is a unit we use in order to give the amount of radiation here. And then we have here the collected charge, and the more charge we collect, that's the better. When the detector is unirradiated, we get quite a lot of charge, but then if the sensor is irradiated, it goes down. So this is something we do in order to show that our fundamental R&D, that our sensors, for example, are okay. Then we move on, we do prototypes. We go to, for example, build small size detectors and test them with real particles. And I will get back to that later on, that the real particles are, for example, at the test beam. And then we do studies of our detectors in that area. Then we have to move on. We have to do larger areas, that we have to place something with more sensors, that we put, for example, this is something like 62 centimeters long, that we have a different number of these kind of modules placed on a larger structure, and that we learn to run not only one module, but that we run a huge amount of modules together. Here only a first step that we do, and then we do a reality check. So we call this, for example, the system test, that we have the, a structure where we put many of those, up to 12 of those together, and then maybe even test that with cosmic rays to see if everything is working. And then only we know that we can actually build a big detector. Therefore, we have important figures of merit. That we test everything very, very detailed. And this is for this tracking detectors. For example, we want to study the signal to noise. We want to understand if the spatial resolution, as I said, we are tracking detectors. We want to test the spatial resolution, hit detection efficiency, and so on. And also for calorimeters, we have to do many studies. And a very important is also to run the full system is a real a trick here. Okay, it seems that I edited the wrong slide this morning in the last moment, but still I think I have all the slides I'm needing. So let's go back to a tracking detector. So the tracking detector is giving a precise measurement of the track in an area and the momentum of the charge. And the momentum we get because of the curvature in the magnetic field. From that, we can calculate then the momentum of the particle. And what is very important for us is that the trajectory should be minimally disturbed in this process. So if we have here too much material, we get a kink in our track that we don't want, because the particle gets deflected in the material. And therefore, we are actually trying to have here as minimal material as we want. And with that, we can then derive backwards to what is happening in the very center, for example, in the LHC, when we are colliding protons to protons, that we have here, for example, some decay lengths, and then we get secondary vertices. We want to measure this very precisely in order to measure these parameters. And with that, we get an image of our particles in the detector. Looking back, there are, since the last 40 years, we have large detectors built, which are getting larger and larger. For example, here is the example of the CMS detector. Okay, so going back to what we have here, we have various silicon detectors from the innermost region, which can be pixel detectors, and we have the outermost region strip detectors. And here I can explain now what are these silicon detectors. So in a pixel detector, as the word says, we have little pixels in the module, in the sensor here. This is a silicon sensor. So when a particle goes through, it makes a signal, and then with that we know where the pixel, where the particle was going through, and with that we get some information which we collect here, and then we have a front-end electronic which picks up through this little connection here, picks up the signal and brings it outside. So a pixel detector is, you have also in your camera of your mobile phone, you have something like a pixel detector, but in our in this area, this is made out of two layers, that we have the front end here separated and the silicon sensor here. This has many channels, which is therefore we can get a high spatial resolution, but it is actually relatively expensive. And in the classic way here with this hybrid, where we have the sensor and the electronics separated out, we actually have a lot of material inside. Then we have the strip detectors here. Which is done not in little pixel and little squares. We actually have the sensor, the silicon sensor segmented into strips, so that we get a 2D information. And there is the possibility that we do on the backside also strip with that get similar like a pixel detector, but we typically have only single-sided strips, which have fewer channels, which are less expensive typically if we are working with one-sided material, but it might be more difficult with less material. Okay, so here is one example of a tracking detector that we have here at the LHC. So we have the protons coming from here and from the backside, and then we have a pixel detector like the first technology I showed you in the very middle. And then we have in the further outer region, we have strip detectors. And here again, the same, again, you can see where the particles are hitting, and then we have a segment where one can see the different layers of silicon detectors shown inside. And only, for example, the silicon tracking detector is made out of many of these modules, which are then little sensors, silicon sensors with front-end electronics attached. Here an example how it looks in the current strip detector in Atlas, that we have this roughly 10 by 10 centimeters large silicon strips, and then we have them segmented in this direction. And then if a particle hits, for example, here in this area, the signal gets moved, the little charge gets moved to the front-end electronics and then read out to the outside world. And we have a second sensor placed behind that, rotated slightly, so that we get additional information of the position. But that's still not like a pixel detector, but still we can get a little bit more information through the second level behind it. I'm just looking at the time that I have, how much time I can talk about this. So here is then again, this drawing I just showed you. We have in the current Atlas detector 61 square meters of silicon. You have to that's a lot of material we used at that time, and it was a few thousand modules which had to be built. And it looks actually here, I like these kind of pictures, that one of these discs is here at NICEF, and they took a fancy picture of it showing how such a disc looks like. So this is 1 meter diameter, and this is like this is 3 meters long, and this is all attached with silicon modules out of strips, and is now in the experiment since 13 years and running. So quite amazing. A few more shiny pictures how something like this looks like. And as I mentioned before, there is then also pixel detectors, and in pixel detectors we have so at some point when we have only strip detectors, we would have the problem that if there are too many particles, that we can't distinguish them from each other anymore. That we have, for example, here you can see easily we can say, okay, this hit. Because we have on both sides of the strip detector, we have a large signal. So this belongs to this one, and these signals are comparable. Therefore, they belong to each other, and therefore we can identify which of the hits belongs to each other. But if there are too many, at some point the strip detector is not working anymore, and therefore we would like to have a pixel detector. That we can track reconstruction at a high particle rate without these problems of these ambiguities. And this was already started in 1983, so before any of the people in the room and in the virtual room were even thinking about pixel detectors. So this is the classic choice in high energy physics, and I will tell you a little bit later what is a non-classic choice anymore. So that we actually have the sensor, so the silicon sensor where the particle goes through, and we get the signal there. Then we have here a so-called bump bond. This is a 50 micrometers connection from the sensor to the readout chip, and then we have a readout chip which reads out the signal, and therefore we know then if that the particle, when it was going through this channel, that we know it was going through this channel, and with that get a 2D position information. They are extremely good. We use them for a lot of experiments in the LHC, and the current version of the LHC experiments, mostly these kind of pixel detectors are being used. But the particle has to go through 2 times this material, and therefore, I said before, material is disturbing the track. This is of course of disadvantage, and we also need quite a bit of power. I will get later to that, what we are doing for next generation pixel detectors in order to improve that. But here, for example, an example, a list of experiments which are using these technologies, and people were working on this for decades in order to improve this. For example, here is how it looks like, that we have a pixel sensor with all these details. So one sensor is this size, and then one places later on front-end chips on this different areas, and with that builds a pixel detector. Here an example how it looks like, that we have then the silicon sensor, which is made out of 2 by 7 centimeters, for example, and then one puts the bump bonds, the front-end chips on them, and puts some on top with glue again, adds some readout possibility so that one can communicate with the outside world. And the bump bonds are indicated here. They are in the order of 25 micrometers big, so they do the connection of the electronics to the sensor. Okay, so if we go to the next generation, and that's why we are talking today, that we are working on the next generation detectors, because the high Lumi LHC will run another, I don't know, until 38 was the last number. We updated the schedule again. I think there is going to be a 40 here in the end. So a really long time we will be running the high Lumi LHC or the LHC, and we are working on detectors now for that. This implies not only that we need, why do we need new detectors is because we will have a higher luminosity, so how many particles we observe in any given moment, how much data we want to take, because that's also a unit for how much radiation we apply to our detectors. And I could not go, because there is only very little time today, I could not go into the details of the radiation damages, but this is one big topic where we work on to understand what are the effects in the sensors and how can we mitigate them. So we will be going from something which we have now, where we have 20 to 25 pileup events, which is a unit how many simultaneous collisions we have. That is what we have currently, and then in the future we will have a factor of 4 more of these. So that means that we have thousands of tracks in one moment, which our detectors have to record, and we have to distinguish later on which track is what. And therefore we need the next generation of detectors, which we are working on now. So we are looking at a bit of a complicated plot now. So this is the 0 point, meaning where the protons hit 0 and 0. And then we have a cutout of the Atlas detector. And here is the radius what kind of difference technologies we are applying here. So we have here the pixels very close to the beam pipe, and then further out we have strip detectors. And there we are going to use different technologies of silicon detectors throughout the whole detector. And this is also a huge area of detector R&D people were working on in the last decade in order to improve all these different sensor technologies in order to have the best pixel detector we can get or the best strip detector we can get for the running at the high Lumi LHC. And we are starting out, I should go back here in the outside. So you have to imagine that this is going to be a barrel around the beam pipe, which is made out of silicon strip sensors. And this we were working on in order to build this kind of modules, so that we have a silicon detector which is segmented along this axis in strips, and then we have front-end chips directly on top of them, glued on a capton, and then connected via a wire bond, which are 25 micrometers thin wires. And of these modules, we have to build in the next years 20,000 modules. So Jens in Dortmund will have a team working on building a few hundred, and at DESY we will build a few hundred. In all around the world, we will build these modules in order to place them together to a large detector. And then we have, for example, staves where we place a number of these modules on in order to make a full length of which goes then along the beam pipe. So here is a bit more on how a module looks like. So we have again a silicon sensor which detects particles, and they are segmented here. Then we glue, so this is an exploded view, we glue that directly, we glue the hybrids. This is a capton material where we put the strips, the chips on top. We glue directly on this silicon, and then on top we put, for example, a power board in order to power the whole thing, because we have to, of course, run at a certain voltage this device. And here are 2 examples how these devices look like for the Atlas ITK. So the strip detector we are working on, that we have the sensors with the electronics placed on top. And here for the end cap region, where it has a little bit of a different shape, but from the concept, it's the same. So we've been working on that quite some time in order to optimize every single step of how to build these modules and sensors, and how to have them surviving the next years. So we use as a sensor here the PN junction made here shown like this. And then I can show you again this plot what we've been measuring over many years, that we have the collected charge versus the fluence, and that we were measuring how does it really behave like, for example, the irradiation level after the high Lumi LHC. And we were always saying we have to be better than 10,000 electrons so that our front-end electronics still can still has enough signal to really work with. Okay. So now we also have to look into pixels. Just quickly, we also want to have pixel detectors, which is a very challenging environment because we are so close to the beam pipe that the amount of irradiation is yet again a factor of 10 more of what the original detectors had to be. So at the time when we were building the original detectors, it was not possible to get a silicon sensor which could survive these numbers. And therefore, another 10 years of R&D was needed in order to optimize this, the material, the sensor, in order to survive this amount of radiation. So what is being planned now is that one has actually relatively square silicon detectors. So one goes for a standard sensor and then has 4 front-end chips, and the concept is very classic, but nevertheless one had to go to a different technology in order to have the better front-end chip, and also the sensors need to be completely different compared to the original silicon sensors. So here people were looking into different technologies. So we call this planar sensor if we are talking about the relatively standard PN junction, which is just a PN junction where the particle goes through. But nevertheless, one had to put a very strong R&D effort into this in order to have this surviving 10 to the 16. Then there is a different technology where one has actually electrodes going vertically into the material, and that one has the PN junctions lateral, which have a smaller distance, and with that one can better apply a high voltage. And with that we actually developed over the last 20 years a technology which is in the end more radiation hard than the classic approach. And by now the industry knows how to do put these electrodes into the material to actually get a reliable connection and a reliable technology, which is now being planned for the innermost layer. Many people were also talking quite a long time about the possibility to have diamond as a material, and also a lot of R&D was going into diamond as a material here for the sensor. And I think when 15 years ago, people were still thinking of having a diamond as a very radiation hard material, but now by now I'm actually saying no, this is not going to work, because in the end one found so many problems so that one cannot build a large area strip detector, or no, sorry, a tracking detector out of diamond. Nevertheless, it's a very interesting material because of its intrinsic radiation material. I think I will skip this slide with all the details on the front-end chip, but nevertheless, also here you can see that a lot of R&D has to go into getting the right readout chip for the pixel detector which survives the high Lumi LHC. And here people are actually going into the direction to really go into 65 nanometer technology in order to have the possibility to add a lot of logic in each pixel to optimize the pixel detectors for the use in the high Lumi LHC. Okay, so now I go to the last part of my presentation, that we need next generation tracking detectors. We want them also for future, for example, for Higgs factory, we are dreaming of yet another tracking detector. And I showed you now the hybrid pixel detectors and the microstrip detectors as we have them currently, for example, in Atlas, that we have a sensor, we have front-end electronics, we have them somehow connected either with wire bonds in the case of the strip detector, or with bump bonds in the case of the pixel detectors. But what do we want? We want smaller pixels. We want to have them thinner because, as I said, the material is disturbing the tracks of our particles. Best would be to get rid of these bump bonds. I mean, they are cool and really doing their job, but it's a lot of material we are adding. Best would be also to get rid of the wire bonds, because even so, this is really a nice feature that we can build these wire bonds. It's really something we don't want, and we want to have finer strips. So the perfect pixel or strip detectors for the next generation would have very small pitch in the order of 20 micrometers or better. We would like to have very thin material. 50 micron would be a nice number, or even better. Best would be to also be able to read this out very fast, get timing information, want to have possibly super radiation hard, and we want to have it, yes, as everything, not only our fridge wants to be smart, but we want to have smart detectors. All in one impossible for with existing sensors. We can't have that right now. We need to work on lower the power budget. We need to compress the data. We need to have a higher in-pixel intelligence, and we want to further understand the radiation damage effects. And at the same time, we of course need to be very cost effective. Our detectors have to be cheaper in the future. And therefore, we are working in the pixel detectors and also for the strip detectors on alternative approaches, that we go away from having the front end chip and the sensor separated out, but that we actually have, we call that monolithic, that we have the front end electronics on the same substrate as the active sensors. And this is not being invented last week, but there are also people working on this since 20 years, that they go to commercial CMOS technologies. Commercial CMOS technologies are technologies, the sensors, not the sensors, the chips you have at home are being made of. For example, the cameras in your telephone, in your smartphone, the camera, that technologies. And therefore, there are already some experiments around which use this kind of monolithic approach, meaning that the electronics, the intelligence is directly sitting on the sensor. We can name there the depth-fed technology from Bell 2. There is Mimosa, which is relatively old in the STAR experiment. And then there is also the Alice ITS. And in this classic approach of monolithic active pixel sensors, so this is what IMAPP stands for, we are using, for example, a imaging process, so a process which is being used for cameras, for digital cameras. We have an epitaxial layer here, and therefore with that we get the small PN junction. In the end, we can use it as a sensor, like in the PN junctions we are currently using. So when a particle is going through, we actually get here some charges, which are then diffusing towards our electrode here, and we can pick up the signal here. And this technology was developed some 20 years ago, but nevertheless, we are still using it, but now in much more advanced technologies. So we were using that, for example, in our test beams for quite some time, and in also some experiments they are showed up in the past. And for example, at DAISY, we are working on a next generation pixel detectors using a technology which is 65 nanometers, where we have also at the first time the access to the CMOS imaging technology. And here we are working now on a pixel detector, which has a much smaller node, and with that we can have many pixels in there with a certain intelligence included. And this is an ongoing R&D, for example, we are working on at DESY. Okay, so here what we are doing is that we, for example, have this first prototype, which is based on this technology, and that we are not only working on simulations of this sensor, that we try to understand what is happening inside in this sensor, but we are also going to test beam with these sensors, and then show how well is this detector working, and understanding the geometry of our pixels and optimizing that, because here the red is the good. Red means that we have a very high efficiency, so that we see a particle almost with 100%, while this bluish area is bad because we don't see very well our particles when they are going through. And this is, for example, a study students are doing in order to, and that we are working on the geometry inside, so that we get rid of these blue areas here. Okay, and then another R&D which is ongoing. This is a little bit older, but nevertheless, this is an interesting future R&D people are doing, that we can actually bend these detectors around the beam pipe, and that would be much more optimal for what we are doing in particle physics. Okay, and last but not least, people are also thinking of how to better disentangle all these tracks here. So a reminder, this is at the interaction point. So the protons come from left and right, and then we have one a collision here, which is the one we are interested in, but we also have a lot of other collisions at the same time, which are then the overlaying, and that we have too many tracks, and therefore we have really a hard time to distinguish that. And if you look at that, here we have X and Y, we have all these tracks, and it's very, very hard to see, because even so they come actually at slightly different times. We have a big we only read out every 25 nanoseconds in LHC, and therefore we have that all at the same time. If we would add timing at the same time, we could actually distinguish then these two different events much better from each other, and therefore getting much better time is of high interest in particle physics. And there is the solution that one has the low gain avalanche diode, that one adds here an additional layer. With that one can add this multiplication layer with a high electric field, and this enables actually that one can get a very fast signal, and with that one can actually have much better timing. One is talking about in the 10 picoseconds or area. 30 picoseconds is currently the state of the art, and we hope to get even a little bit better in the future.